the chemical charge of the polymer is enough high, there is a threshold, and of course there is an instability, and to avoid this instability, some contrails are condensed onto the macroelectrolyte. Also, you can classify these polyelectrolytes, so chemists classify the polyelectrolyte as polyanion and polycations, but for physicists, you have to compare, it's more important to compare weakly charged polyelectrolytes and highly charged, anneal polyelectrolytes and quench. We will see what that means, and hydrophilic with respect to hydrophobic, flexible with respect to semi-flexible, linear with respect to branch architecture, and saturated with respect to conjugated. Normally, all the red color correspond to what I would like to present you. So if I take the example of the sulfonated polystyrene, which is the main example of polyelectrolyte, it's this highly charged polyelectrolyte. You know, here you have the phenyl in the gamma position. Here you have replaced the hydrogen atom by this SO3 minus ions, and you have quintiles, and the quintiles could be monovalent or divalent, and you have different monovalent quintiles which can be used, you know. Some quintiles can be deuterated, that is important for neutron scattering, and the macroion can be also hydrogenated or deuterated. The degree of sulfonation is quite important. It is the chemical charge fraction, and this chemical charge fraction, because it is a quenched polyelectrolyte, is controlled by the chemistry. So here, when you put the charge along the chemical sequence, of course, that's the work of the chemist, not the work of the pH of the solution. So you have no fluctuations, and also the distribution and the charge fraction is fixed. Also, you can see if, on this example, these monomers, the sulfonated monomers, is soluble in water, but the parent monomer, the styrene monomer, is not soluble in water. So if you vary the degree of sulfonation, of course, at low degree of sulfonation, here, until 30%, the polyelectrolyte is insoluble and is perfectly soluble after. But of course, it is only hydrophilic when you have 100% of sulfonation degree. If you reduce this sulfonation degree, you introduce some hydrophobic effect. So it is an example of a hydrophobic polyelectrolyte, a quench one, if provide the sulfonation degree is less than 1. Okay? It is important because you have also some anneal polyelectrolyte. In this case, the distribution of electrical charges along the chemical sequence is fixed by the pH. Usually it's a weak acid. We consider a weak acid, not a strong acid like here. And for carboxylate groups, for example. And in this case, of course, there is some fluctuation in the position of charges. And this fluctuation could have some importance. They are not important when you are in the hydrophilic regime, but when you are going towards the hydrophobic regime, when you reduce the electrical charges and you increase the hydrophobic effect, in this case, the quench and the anneal polyelectrolyte behavior are distinct. We will see, I hope. Of course, here, there is another point. Of course, it's an hydrophobic polyelectrolyte. Why? Because if you have an hydrophilic polyelectrolyte, of course, when you increase the chemical charge fraction here, in this case, you have an effective charge which is proportional, which is directly equals to the chemical fractions, until a certain threshold, a certain chemical fractions. Beyond this chemical fraction, due to the condensation of Coulomb ions on the macroion, the effective charge will not change. Okay? If you have an hydrophilic polyelectrolyte and purely hydrophilic, when you change the chemical charge fractions beyond the Manning-Ozawa threshold, you have always the same effective charge. But you see that when you have an hydrophobic one, it's not the case. Okay? It's not a plateau here, but you have nothing until a certain, it is here, after 30% for the degree of superposition or the chemical charge fraction. In this case, you increase slowly the effective charge. That's an important thing. For the small angle scattering, of course, the previous speakers has described some things, you know, but it's very easy. What you are measuring with this technique, it's you have a detector. I only consider the static scattering, and you measure the scattered intensity here, so the number of scattered particles at different scattering angle. Okay? And when you are in the static approximation, so you assume that there is no energy transfer in between the radiation and the matter. In this case, you have the difference in the wavelengths of the direct beam and the scattered beam is defined by something which is close to the Bragg law, you know. So what you are measuring is the scattered intensity. Practically, you measure the scattering intensity versus the scattering angle, but of course, the parameter which is significant, which is important, is the scattering vector, or Q, and this scattering vector is, of course, proportional to the scattering angle if you are at small angle. And because I am considering large particle in the real space, I will observe small Q values, so small angle, okay? The formalism of this technique is very simple. It's the linear response theory. You know, you measure some correlation functions, some correlation function of the density. I will make some comments. The previous speaker speaks about density fluctuation, but me, I will speak about concentration fluctuation. So, at small angle, for example, you can neglect in the first approximation the density fluctuations, but you have, if you have a solute in a solvent, you have the concentration fluctuation. And this concentration fluctuation gives you information about the structure. I would like to emphasize also that because the polyelectrolyte has two components, of course, you have three distinct scattering functions. One for the macroion, or the blue particles here, the monomers, and you have the same for the contour ions, and of course you have the cross tail. Okay? So from these partial scattering functions, depending on the technique that you use, you will see mainly, for example, the macroion. That is the case if you use the small angle neutron scattering. But if you use small angle X-ray scattering, you will see both the macroion but also the contour ions. In any case, with the small angle neutron scattering technique, you can also use the contrast variation method, which is very easy. You use the leveling by replacing hydrogen atom by deuterium to change the factor here, the contrast length of the macroion with respect to the second, or the contrast length of the contour ions with respect to the second. Of course, if you, for example, if you use the deuterated macroion in the D2O, you have a chance, and if you use also hydrogenated contour ions, you have a chance to observe only the contour ions. Of course, from this partial scattering function, you could also have some information about not only the density or the molecular structures, but also the dielectric structures. So you can also extract what we call, the theoretician call, the charge structure functions. Finally, here, you see that you can have, for each partial scattering function, of course, you have intramolecular terms, so the correlation in between, for example, the monomers inside one chain, but you can also have the intermolecular terms, so the correlation in between monomers belonging to two distinct chains. Okay? I give you an example. Here you have the scattering from the polyelectrolyte solutions. If you have no added salt, you will observe a maximum here. If you added salt, of course you screen the electrostatic interaction in between the monomers and in between the macromolecules and the macroion. In this case, this peak disappears. Okay? If you have a neutral macromolecule, if you increase the concentration, of course you increase the intermolecular term, but you have never this kind of peak. It's only due to the long scale of the electrostatic interactions. But to observe this maximum, which is characteristic of polyelectrolyte solutions, you have to avoid any added salt. So, here you have the first result. If you have, you look at the scattering intensity versus the scattering vectors, you have this maximum, and of course the position of this maximum changes with the concentration. But not only with the concentration. But of course, that has been observed for the first time by these two persons, Coton-Mohan, and everybody has seen this maximum now. So, but the first explanation was given by De Gene. And you know, when you are in a dilute solution, of course the monomers are well separated. In this case, of course, this maximum has something to do with the position order. So, if you want, if you take the position and you take the inverse of the position of this maximum in the Fourier space, you obtain the average distance in between the macromolecules. You have a position order. But when you are going towards the semi-dilute regime, so when the macromolecules begins to interpenetrate like that, like my fingers, like that, you know, you see you have a sort of temporary network. In this case, there is no position order, but you have some mesh size of the network. This mesh size is the correlation length, and of course, has nothing to do with the position order. It's only like what we call a correlation pole. So, around one macroion here, there is some volume which is forbidden for another macromolecules. It's like the art sphere. If you put art sphere on there, you have a peak when you increase the concentration, but this peak does not move because it's related to a correlation hole. But in the case of the polyelectrolyte, of course, this correlation hole, the volume of this correlation hole, the volume depends on the concentration. Why? Because it depends on the ionic strengths, it depends on the device screening length. Okay? So when you change the concentration, you change the position, because the correlation hole, its volume changes with the concentration via the device screening length. Okay? So you see, you have a peak, but you have no order, no translation order, no orientation order. You have a perfect disordered system. Now, of course, by the position of this peak, you measure what we call the screening length, but the screening length has something to do with the device screening length in some aspect. So now, if you look at for different macroions, different Coulter ions, and you plot this position of this maximum with respect to the concentration, you see you have some dispersion here. Of course, the theoreticians have proposed some scaling law approaches, and specifically Dominique Colby-Rubinstein has proposed this value, this relation in between the screening length correlation length, and the concentrations, and the effective charge. Okay? So we are able to compute the effective charge for any polyelectrolyte, assuming the Manning-Ozawa condensation model. And when you do that, you compare the, yes, of course. If you compare here, it is the position of the electrostatic peak versus here the concentration, and there is a dispersion. If you replace the concentration here by the screening length here, so you have some universal law if you want. Of course, I am sorry, but it's a problem of the PC, not the Mac. Here, so you see that the scaling law proposed by Eugene first and by Dobrynin and co-workers works. There is some, of course, there is again some dispersion. Why? You could, you could understand that first, the form factors can have some influence on the position of the peak that you obtain from the total scattering functions. For example, here we have performed different experiments, and for the reg 1 here, you have a contrails which is hydrogenated, and and the macron which is deuterium. So when you are in D2O, you see mainly the contrails, and when you are in H2O, you see mainly the macron. And you see that at small concentration, if you compare the partial scattering function of contrails and macron, the peak is reasonably at the same position. But if you increase the concentration, you have some differences. Another problem, if you want, here. So you are able to measure the effective charge by the position of this electrostatic peak. That is demonstrated here. Here we have used mixtures of monovalent and divalent contrails. That is very simple. You mix two kinds of salt form of styrene sulfonate, polystyrene sulfonate, and you obtain a change in the contrails. The contrails are either here for this variable 0 here, you have mainly the calcium contrails, and here you have mainly the sodium contrails. Of course, the condensation is not the same, so the effective charge is not the same for monovalent and divalent contrails. I don't entry in the details, but you see that, of course, you expect some figure like that from the Manning-Ozawa, because when you mix divalent and monovalent contrails, first you condense the divalent. Okay? Here you see the maximum at small concentration is almost the same shape of the curve, you know, because here you plot the position of the maximum versus the x value, so the proportion of monovalent contrails. Of course, nothing is perfect, so here you see you have, I don't know what that. Sorry. Here you see when you increase the concentration, here, the shape of this curve, the Q star versus the fraction of monovalent contrails, changes. And that is cannot be explained by the Manning-Ozawa model, because the Manning-Ozawa model proposed some strange curve like that. But you can explain that using another model, a mean field model, a mean field which is the Poisson-Boltzmann. And if you solve the Poisson-Boltzmann equation to obtain the effective charge, you will obtain that. You see, and with the concentration, the curve initially in the limiting law of Manning-Ozawa, you see it's very smooth. So you have this problem with the concentration. In any case, you don't explain all by the Poisson-Boltzmann equation and theory, of course. It's only a mean field theory, so you cannot explain all. But you explain something. So you see, From the Manigozawa model, there is no agreement in between the theory and experiments, and with the possible span. Also, I would like to emphasize that if you compare the acid form of the polystyrene sulfonate and the salt form, you have a change here on the effective charge. I don't want to go into details, but of course, if you consider the proton, the Coultrian H+, it is more condensed than the Coultrian sodium or even the Coultrian cesium. That it's probably due to not only the ionic radii, it's probably due to some also hydrogen bonding. No, and that is an agreement. So you see here, I am in the dilute regime. The Q-star vary like C2 1/3. When I go in the semi-dilute regime, Q-star vary like C2 1/2. If you are in the concentrated regime, you have Q-star which vary like C2 1/4. That, I don't explain that, but it's very easy to explain. In this case, the thermal blob, the electrostatic blob, corresponds to a certain concentration. You can assume that the macromolecule is almost Gaussian. But that regimes, each regime is characterized by a scaling law. It's very simple. You have an exponent which characterizes the regime. And you see that these three regimes here, dilute, semi-dilute, concentrated, was well described by theory and also has been relatively observed by the experimentalists. And when you go beyond the concentrated regime, when you increase the concentration, when you go to the melt. In this case, you have the case of the swollen regime. The swollen regime has been proposed by Nishida first, and I would like to discuss that now. Why? I would like to discuss the existence of an orientation order in polyelectrolyte solutions. Until now, nobody has observed any orientation order with flexible polyelectrolyte. But normally, if you have anisotropic particles like that, you have at low concentration in isotropic solutions, but if you increase the concentration, you have some compactness arguments which lead to some orientation order like that, elegant, like some symmetric liquid crystal. But to go from isotropic to the nematic, if you want, regime, you have the Onsager transition. Onsager has predicted that in 1949. And all has been observed with the virus, the tobacco mosaic virus by Kyiv, and also by some bacteriophage, by Fraden and Grelet, and also by some short DNA. Okay? And what happens when you consider long polyelectrolyte, but with some local stiffness? That is my problem. So I give you a summary of that, because I'm not sure that I can go until the end. Well, you see, I will tell you that I want to emphasize the importance of the intrinsic stiffness of polyelectrolyte. The behavior of the polyelectrolyte peak is the signature, the fingerprint of the regimes, of the structure. So you have these two regimes, which has been observed in the past, and that, of course, if you use another polyelectrolyte with an intrinsic stiffness higher, in this case you observe two other regimes. Q star very like C, proportional to the concentration, and after it is proportional to C to 1/1/2. So here you have two regimes which are distinct of what was predicted before by theoreticians and even by experimentalists. And of course, this regime, Q star proportional to C, is like a metastable regime, you know, at high concentration you observe some nematic phase. You can observe some birefringence, but in fact, in between cross polarizer, you are not able to observe any texture, classical or nematic phase. It's because the domains are very small, I think so. But you see a small birefringence, and you observe the Q star, which very like C2-1-half. But just before, you have the mixtures, and of course, it's like a metastable phase. It is a jam random close stacking of equivalent solid rods with the length comparable to the length 166. So you see, I would like to emphasize that this nematic phase was predicted by Yarkova and co-workers, and also by Karim Tukuma, but they only predicted this phase. They have not predicted this quite strange regime where the maximum is proportional to the concentration. So, we have used different polyelectrolytes with different angiotensive stiffness here. For example, here for the polystyrene sulfonated, you have 10 angstrom for the naked persistence length. If you go to the polydenmark and other polyelectrolytes, polycations, you have 30 angstrom. And if you go further with the hyaluronate, for example, you have some things which is twice the polydenmark. So, I give you some small angle X-ray scattering results here. So you increase the concentration, so the peak moves here. It is the electrostatic peak. So when you increase the concentration, because you increase the ionic strands, of course the peak disappear when you increase the concentration. But at a certain concentration, you have another peak. It's always a correlation hole. This peak here is much more a steric correlation hole, not an electrostatic correlation hole, if you want. And in this case, you can see that, of course, that could be, there is another behavior. It's not so easy, but you have another behavior, you will see. At high concentration, you observe what Nishida has observed before. So you have some ionomer regime. I don't want to speak about that. So you see, you observe C2-1-half, C2-1-4, and after something which is a pure ionomer regime, because you have decreased the dielectric constant of the solution, of course, and so you have dipoles here, and you have some association in between these things. But you know, when you know, now if you use polydenmark, you have the same, but the contrast is lower, of course. And what you are able to observe, you observe the semi-dilute regime as well as you will see with the small angle neutron scattering, but you see you have this Q proportional to C here, and after the nematic regime. How you can explain that? Of course, I consider only the exclude volume between two rod-like molecules here, and the distance here, the exclude volume, is proportional to the length of these objects and to the diameter of the cross-section. But here, the diameter corresponds to the closest distance on approach, so it corresponds to C, let's say that C. And the compactness imposes this relationship on this one. So if you have this geometry here, you have this closest distance of approach, which is inversely proportional to C. And when you consider this, you have, which is proportional to the inverse of the square root. So you see, when you have electrostatic, this configuration is the most probable configuration, of course, because you have a strong regulation. If you consider the compactness, the Onsager problem, of course, the best configuration is that. So you see with polyelectrolyte, you have some frustration in between these two interactions. So, of course, when you increase the concentration, the electrostatic interaction decreases, of course, but you have this combination of the electrostatic interactions and the compactness argument of one second. And that is why you observe this metastable regime in between the concentrated regime and the nematic phase. And you see, in this case, you don't observe any uniform approach. I finish 1 minute, sorry. Here, there is a comparison in between results obtained by small angle X-ray scattering and results obtained by small angle neutron scattering. It's quite interesting because, well, my knowledge, is the first time that I see the influence of the labeling of the contrast on the intermolecular term, not on the intramolecular term. Usually the effect is on the intramolecular term. But here it's an effect on the intermolecular term. And it's only related to the fact that the contraions are much more mobile along the polymers. And when you consider the contraions, of course, the excluded volume is reduced. So the position of the maximum is not at the same position that if you look at only the macro wave. Okay? I finish once. If you put salt, if you add salt, in this case, you suppress the electrostatic interaction. And you see that if you suppress the electrostatic interactions, of course, this regime, Q star proportional to C, disappears. You favorize the nematic regime, of course, because you kill that. You have only that. Thanks, I finished here. I'm sorry. Here you see, okay. I will stop here. You see, with the hyaluronide, the contraions, there is no, if you want, you have no condensed contraions. And in this case, if you use X-ray, you see only the macroion, because the contraions are in the solvent. And you can compare that with the polydenmark, but in the case of the polydenmark, you have to use neutron to observe only the macroion. Okay? And when you compare that, you see, of course, first, the regime, the jam regime appears when you obtain the Q star close to the persistence length, but you see also that you observe the difference in the persistence length, the naked persistence length, so the persistence length, the non-electrostatic persistence length of the two polymers. That's all. I'm sorry. Thank you for your attention. That is open for discussion. Question, please. You're welcome.
Yes, you said correlation hold. Yes, can you a little bit please explain it? It's just due to electrostatic properties of polymer, or it's also you can use it for normal polymers non-charged? And did you have it from your experiments?
I'm not sure that. Of course, if you have neutron polymer, you can observe some second condition. I only show here that if you have polyelectrolytes and flexible, semi-flexible electrolyte, if the electrolyte is too flexible, in this case, you have no on-second transition. If the polyelectrolyte is very stiff, you observe on-second transition. That is the example of the bacteriophage and even of tobacco-virus. But, of course, here when you have semi-flexible polyelectrolyte, the electrostatic involved, you observe this jam regime only because you have competition in between the electrostatic, which favorizes these configurations, and the compactness, so the insider condition, which favorizes this parallel configuration. With an equal electrolyte, you are not that. So you will not have this metastable phase if you want.
Correlation hole. Can you go correlation hole? You remember you told us what correlation hole?
The correlation hole, for example, if you have a particle here,
Yes, I understand. It's like you have to talk. You cannot like throw another particle in this.
if you have art sphere, for example, the correlation hole you cannot interpenetrate. So it corresponds to the bubble of the radius of the sphere. It is a hole, a volume, which is forbidden for the other part.
Actually, it's like.
And there is no other, I insist about that. You know, if you have some ball on the table like that, you know, you have no other, but you have some peak. If you increase the concentration, you will observe a peak, and this peak has nothing to do with any position of it.
And as an
Yes. As far as I understand, according to your point of view, the proton is the hydrated proton is bound better as compared with sodium ion to the sulfonate polyelectrode. Yes,
Yeah.
but
Why? I don't know precisely.
the ion exchange constant between these two ions on the surface of ionic surfactant micelles is close to unity. So, is really such a difference between ionic micelle surface, so phase,
I think that
sulfonates,
it's a
and
difference
the
between
polyelectrode?
electrolyte and
Yes.
micelles, if you want. I don't know the case of the micelles, but it's clear that if you compare different monovalent neutrons, usually you have no difference in the position of the Q star with respect to the concentration, because you have almost the same effective charge. Almost the same. There is no,
Yes.
what is the name of this crazy biological effect? But if you take the hydrogen, if you take proton with respect to the monovalent neutrons, in this case, you have a change in the effective charge. That's an experimental result. I don't know, I have not looked for to understand more, but I think that that could be related to the ionic radius, but it's not enough. You cannot explain all by the difference in the ionic radius of the neutrons between sodium and hydrogen. My only explanation is that you have some additional bonding, H bonding effect. That's all.
The sulfonate group stayed unprotonated.